So today we're going to talk about three free body diagrams. Free body diagrams are really important in statics and in engineering as well, just because it provides the viewer with something to go off of how the forces are acting on an object. But we'll get into that a bit more later. So a free body diagram is a sketch of an object or part of an object that has been removed from its surroundings. To make a free body diagram, we want to cut the specific object or part of the object from its surroundings. Then we want to draw all the forces which are acting on the particle, and usually we can treat it as a particle, but we'll get to that a bit later. Then we want to label all forces and provide magnitudes and directions if known. So what we want to keep in mind is we want to make neat and scaled diagrams, only if possible. If there's one force that is massive compared to the rest, we can't scale it properly. And if there are no moving parts within the free body diagram, so nothing is moving relative to anything else, we can treat it as a point or particle. So a kinetic body diagram is pretty similar to a free body diagram, but it only shows the net force. So it shows force due to acceleration, just the net force. So net force, of course, is if you were to add all of the forces, then you could find the net force, and this is the only force that is labeled in the kinetic body diagram. For bodies in equilibrium, there's no net force, and thus there are no forces in the kinetic body diagram. Equilibrium can also apply to bodies in motion as long as there's no acceleration, such as a body that is undergoing just velocity, and with no acceleration, no force. So for an example, we're going to draw a free body diagram and kinetic body diagram of a 20 kilogram box at rest hanging from a string. And we'll also look at an example of a body in motion, but still in equilibrium. So first the box. So we have a box. And it looks a little bit like this. So we can then imagine this as a particle in our free body diagram. So there's our particle. We know that there is a tension force due to the string, as well as a force of gravity. And these two happen to be equal. So we know that force of gravity is, one other thing that's really important is we need to define our direction. So in this case, I'm going to define up as positive. So in this case, we have a 20 kilogram box times negative 9.81 meter per second squared acceleration, which is equal to 196.2 newtons, which is negative because it's going down. And this means that the tension, since it's the only other force and they will cancel out, since the body's not accelerating, is 96.2 newtons as well. So then we can draw our kinetic body diagram. And this will just be a point because there is no net force. So the tension and the gravitational force are the only two forces, and they cancel out, meaning that there is no net force. And that is it for the kinetic body diagram. So that's everything for today. I hope you enjoyed. Thank you again to Loom and Google Keep and to my professors. And I hope to see you again next time.